The DTP4500 is an SCA-compliant, high-performance, software-defined radio development and test platform. The DTP4500 covers 225 MHz to 4 GHz RF with a fully programmable contiguous signal bandwidth of 50 kHz to 20 MHz and supports fast frequency hopping waveforms. The platform supports current SCA standards and next-generation complex SCA-compliant waveforms, all with a small form factor, low DC power consumption that enables the development, testing, and deployment of a waveform. The DTP4500 enables advanced SDR and waveform development on an affordable SCA development and test platform. The platform configuration includes a Mistral OMAP35X board providing baseband processing resources including general-purpose processor and digital signal processor, the DataSoft Monsoon RF transceiver providing FPGA resources and RF functionality, PrismTech's benchmark setting SCA 2.2.2 compliant operating environment that includes a core framework, radio services and devices, Object Request Broker, Corba services, Wind River's VxWorks real-time operating system, device drivers, and board support packages. Also included is a demonstration SCA waveform application, documentation, all available off the shelf with simple licensing and support. Typical uses of this platform are radio OEMs and their customers providing a quick start SCA development environment in advance of later deployment on target production radio platforms, academic institutions for teaching and laboratory use, wireless communications research laboratories, and internal research and development projects. This is the software stack for the DTP4500. The red triangles indicate the entry-level components. The capability of the product may be extended with several options. Starting on the Mistral EVM, the entry-level system components hosted on the GPP are the VxWorks RTOS, the Spectra eOrb and core framework. The platform is integrated with radio services, an HTTP server for human-machine interfaces, and a demonstration waveform for a working platform right out of the box. For productivity tooling, Workbench is included as an entry-level component. We do recommend the Spectra CX option for SCA code generation and validation. This slide shows the hardware architecture of the DTP4500. Again, the red triangles indicate the entry-level components. Starting with the GPP DSP, we use the Mistral OMAP35X EVM with TI C64X DSP and ARM GPP. It includes audio and Ethernet connections for high-speed digital interfaces. The option to extend beyond baseband to RF is provided with the DataSoft Monsoon transceiver. The transceiver includes an FPGA integrated with the GPP and DSP processors. The transceiver is intended for laboratory environments. If the need arises to extend testing to an electromagnetic environment, families of front-end modules are in development covering RF frequencies from 400 MHz to 1 GHz.
This is Spectra CX, and in this SCA project we have created two models, the DTP4500 platform and the example waveform. First I will show you the platform. The top level diagram shows the DTP4500 platform, which consists of only a single node. If we open the diagram for the node, it will give us the details of what components exist in the platform model. You can see 7 components. In the assembly we have an instance of domain manager. So at runtime when we start up a device manager for this node, it will automatically run the domain manager. We have the standard log service here, and we have the device manager itself. We also have an executable device, which in this case is a standard binary executable device that we ship with our core framework. Since this is a binary that we have pre-built and shipped, so we're not going to be generating code for this. We have an audio port, which implements the functionality needed to interface with the audio output capability of the DTP4500 board. We have a stream of samples that can be sent to the audio port device, and the audio port device is able to use a stream control interface for flow control. I'm able to show you more detail on the audio port device and look at the actual definition of this component. Here is the component interface for the audio port device, and this corresponds to the SCD, so it defines the ports, one of which provides a sample stream interface and the other one which uses a sample stream control interface. It also directly supports the core framework device interface. In the device implementation, there's operational code which I'll show you shortly. We have also modeled the binary itself. We have two variants of the binary, one which is built with the release flags and the other built with the debug flags. Currently the model is set up to produce the release version of the binaries. We also have two other devices, specifically the waveform FPGA proxy and the RF control devices. The WF FPGA proxy device provides an interface for the waveform to send and receive data from the Monsoon RF subsystem, and the RF control device which can be used to control the Monsoon transceiver hardware. Again, both release and debug versions of these devices are modeled and can be generated from the tool. The devices currently in the platform for which we actually generate code are the audio port device, the WF FPGA proxy, and the RF CTRL devices, as these also all contain handwritten code. The other devices in the platform model, such as the device manager and domain manager, are models of pre-existing binaries that are part of our core framework. We've included a model of these components, but are not going to generate code for them. We're simply going to generate the XML descriptors and make use of them in the platform assembly that we just saw. When we deploy the files onto the target, we will just pick up the pre-existing binaries. The only device currently in the platform for which you actually generate code is the audio port device, as this contains handwritten code. So that is the platform model. The example waveform that I can show you now has a little more content. This is the assembly which corresponds to an SAD file. This contains instances of file input component, which currently uses the file manager to read audio files off of the core framework file system. It then pumps the audio samples to the use sampler component, which upscales the samples from 16 to 48 kHz, before pushing the samples to the mod component, which modulates the samples in the transmit direction and sends them to the Monsoon transceiver via the WFPGA proxy device. In the transmit direction, the WFPGA proxy device pushes I and Q samples from the transceiver to the demod components, which will then demodulate the samples and forward them on to the resampler. The resampler will downscale the samples from 48 kHz to 16 kHz and then send the samples to the audio port device in the platform. All four of these components are controlled by the assembly controller component, which you can see in the middle. In contrast to the platform model, these components are going to be code generated and will contain some handwritten code. So let's look at the file input component in an example. Again, we have modeled both a debug version and a release version of the binary. If we take a look a little bit further into these models, we can see in the build configuration that this deals with the compiler flags and so on. In the debug version, you can see that we have added the extra flags to allow us to compile in debug mode. This is what these two different implementations are modeling. Again, in the application, we are currently set up to use the release binaries. Now I will generate the SCA descriptors and structural code for the platform and waveform models. We will switch back to the platform and generate the descriptors and code for any components where we are not using precompiled binaries. In this example, this is just the audio port device, the WFPGA proxy device, and the RF CTRL device. The code and descriptors have been generated for the 4500 platform. As you can see, it has produced this generated source project. Now I will do the same for the demo waveform. And that completes the code and descriptor generation. I have generated two source projects, one for the platform and the other for the demo waveform. In my targets view, I can see my targets in the make files. I will start with the platform and will compile all of the source files. In the case of the platform, this involves compiling the core framework IDL, all device interfacers, and obviously the devices themselves. This is running a generated makefile which invokes the VxWorks toolchain and the Spectra orb IDL compiler to build the libraries. The remainder of the components in the platform model are precompiled binaries that it will pick up out of the core framework. Now that it is finished compiling, we can take a look in the project, and we should be able to see our audio port device, WFPGA proxy device, and the RF CTRL device binaries. I'll do the same for compilation on the generated demo waveform model. This is exactly the same, except it would hold more components. All 5 components in the application are generated and compiled, so this compilation will take a bit longer. The next step will be to gather together the binaries for the platform components, along with the descriptors for the application assembly and components, into a deployable set, and actually deploy them onto the DTP4500 platform. As a result, when you power on your DTP4500, it is going to automatically boot VxWorks and then boot the SCA platform model that is shown on the screen. Now that the DTP4500 is powered on and the platform is running, I can connect to the Spectra CX SCA runtime monitor to my board, where we can actually see the platform running. I have this monitor object in the model which contains details of the board and how to connect to it. You can see that it does not display the device manager and domain manager, as they are implicit. If I open the SCA monitor, it will connect to my board and display the actual running platform. What you can see are the audio port device, the WFPGA proxy device, the RF CTRL device, the executable device, and the log service that we saw in our model. They are actually deployed and running on the DTP4500. What I've also done is deploy the descriptors and binaries for the application model, which we generated and compiled earlier. I've copied those onto the target file system of the DTP4500. There are many ways of getting the files onto the target. You can use NFS if you have that built into your VxWorks kernel. You can even unplug the USB card and connect it to your host to copy the files. I have simply transferred them onto a USB stick. What I can do with the runtime monitor at this point is install the application factory, and what you'll see here is the runtime monitor has inspected the file system and found the SID file for our demo application. If I choose that, it will create the application factory corresponding to the SID file, which it has done, and now the factory is available to create application instances. Now I can create instances of the application. If I switch to the terminal, we should see some output from the application factory as it creates the application. As I mentioned previously, I've already deployed the runtime versions of the binaries, so there is not much output from the binaries. Now we have an instance of our application running on the DTP4500. So we can see if I switch back to the application assembly model that we have the file input, the mod, demod, resampler, and assembly controller. The monitor is connected to the running system, and we can now see the instances of those components running on the target. When an application is created, it is not initially running. We have access from the runtime monitor to the lifecycle operations through which we are able to start the application. Before we can start the waveform and transmit a signal over the air, we must configure the transmit frequency of the RF CTRL device. In this case to 446.000625 MHz, and also set the value of the file transfer enable property to be true on the file in-out component. If I switch to the serial terminal after I've started the application, we should see the audio port device is printing out a dot for each sample that it receives, and the DTP4500 is actually transmitting the audio signal over air. I can stop the application and you can see that the processing has ceased, and then from the SCA monitor I can also release the application, and here you can see the application instances have disappeared. You can also see that there has been some activity unloading the application. I can also uninstall the application factory itself, and now I am back to a bare platform running on the DTP4500.
What I'm going to show now is essentially the same process of connecting to the DTP4500 and deploying an application. But this time, instead of using the SCA monitor in Spectra CX, I will perform all of those actions using the OE admin tool that comes with the Spectra core framework. I still have the DTP4500 board running, and it is running the platform model. I have a terminal connection to the board, and I am now able to run the OE admin executable. This is a tool that runs on the target itself and is a very small textual based tool. You need to give the OE admin tool a reference to the name service so it can look up the domain manager. So if I type that core block in correctly, what you can see is the main menu for OE admin. The first thing I can do is the view command, which will display all of the domain objects. You can see the domain manager and its ID, no application factories and no applications. We have one device manager under which we can see the audio device, the executable device, and the log service. These elements comprise the default DTP45 platform. We can now install an application. I type in the name of the SAD file that has installed the application DTP4500 fm.sad.xml. If we view the domain objects again, we should now see an additional application factory for the DTP4500 FM waveform. Now that I have an application factory, I also have new options on the menu. For example, I can now create an application. I choose Create. I choose the application factory, which is number 1. Type in a name for the application instance. I will call it A1. And now it will create an instance of the DTP4500 FM waveform. And now that we have an instance of the application, if I do a view of the domain, I can show that we now have A1 under Applications, under which we have the 5 resources. At this point, I can start the application, and I will choose A1 to start. Now if I switch to the other console, I can see the dots again from the audio device processing the samples. So if I now choose to stop the application, I choose A1 as the application to stop, and then on the console you can see the dots have stopped, so the application has stopped processing. Now I can release the application, application number 1, which will tear down all of the components. I can then uninstall the application factory, and I will choose our DTP4500 FM waveform. Again, I should be back down to the base platform with no applications or application factories installed. If I do a view, I can see the domain manager, no application factories, no applications, and our device manager with the 2 devices and the log service. That is a quick demonstration of the OE admin tool. One key thing to remember is that this tool runs on the target itself. Therefore, it can be a little unresponsive when applications are running and consuming CPU time. But it is useful, small, written in C, and uses the eOrbC to communicate with the core framework. So, it is very small and lightweight, can run on the target, providing administration over the serial port.